Hello and welcome to the segment 3 in this week. So in this segment we will talk about more in the graph execution of the TensorFlow. So TF dot function decorator that we have seen in the last class. So in this segment we will go deeper into the graph execution and TensorFlow optimization, because here any hot function in the training pipeline that you see we will try to run in this TF dot function decorator, right. So that's what we discussed, and what the performance improvement that we can get, that also we have demonstrated. But what exactly goes through while executing this function decorator under the hood, that we will look. And also we will talk about autograph, because while forming the graph it's bit different when you write the Python code, let's say the branches, the loops that we execute in the training pipeline. So all these things, if we try to write in the Pythonic way, and that will be different whether we are trying to execute in eager mode or in graph mode. So autograph will automatically transform this kind of functional structures inside your code into graph structure, and that's what we will see. And then the tracing and the profiling and also few optimization techniques that we will study. So TF dot function decorator that we have seen, we talked about a lot. So this decorator that compiles a Python function into a TensorFlow computation graph, right. So first call traces the function and builds the graph. So when this function is encountered at the first call, it will see that it has this function decorator, and basically it will form or build the graph which is defined under this function definition. But when the subsequent calls will be happening, obviously that will execute this particular compiled graph. So no longer compilation will happen basically, right. So no Python interpreter will be involved in the subsequent call. So that will actually give you the performance boost. Usually we get 2 to 10 times faster execution than the eager mode that we have seen. Now what exactly this graph is, because this graph will also lead to this autograph concept, right. And basically any hot function that you try to engage into in this TensorFlow. So we will go into the particular function and we will try to see exactly what this functional graph is. So eager execution here in this particular page, you are seeing that left hand side is basically the eager execution, where we have this line 1, line 2, which is executing y equal to x power 2 and z equal to y plus 3. So now these two lines essentially getting executed exactly when it is the interpreter is executing. So you will get the output automatically in this line itself, where you have this next line to this second line. Now in the graph execution, it traces the Python code once. So it goes through the Python code once with this TF dot function decorator, and then it builds the computation graph, and then in the subsequent calls it actually uses the cached graph that is already cached into this building computation graph stage, and then it reuses this particular graph. So no more compilation happens, and then you have the optimized code running in the backend operations. So usually this happens in C++ in the backend, but you get the idea. Now when this will be cached and when this will not be cached, that will actually provide the performance boost, because then this tracing mechanism will come into picture, the tracing concept, and obviously the signatures. So essentially what happens is that if you see this particular line, what exactly mentioned in this particular handout is that trace the function first stage. It traces the function and runs the Python code once to record operations into a TF dot graph. So I have operations into these functions. For an example, in this particular function, under this decorator, I have this traced fn, which is having few functions to make. So it is actually doing an log appending. So basically a list appending, it's happening, and another printing is happening, and then it's doing the reduction of this squared of the elements and returning the reduced sum from this function. So, this is the exact operation that is happening, the sum of squares, and then logging is happening, right. So, here you are appending to the log, but this log is basically a Python log. Okay. So, these two differences we will come into a few moments later. Just try to understand first what exactly this graph is all about. So, when we write one operation, let us say y equal to ReLU x times w plus b. So, now here what is happening? Here we are having this ReLU computation over the linear transformation that is happening here, right. So, now this will be defined by this matrix multiplication, right. So, input x and w matrix and weight matrix here, and then the bias will be added. So, you can see that this input x and w is getting into this matmul operation node. So, now you can see the graph happening, right. So, here we have the operation node where inputs are coming as tensors. So, basically these edges are TensorFlow, tensors are flowing through the edges, and then the operation node will give you the output of the matrix multiplication operation, and this will go into this ReLU. So, now this ReLU will also take the bias, which is basically bias add operation, right. And then after the bias add operation, you will have this output of y, right. So, now this graph has branches, and these branches it can merge the branches, it can capture data dependencies. So, this data flow or TensorFlow graph is basically defining how the tensors are flowing through different operations that are happening inside this function which is developed under this decorator, right. So, this is exactly this function, whatever function you are doing here, right. So, now the caching will happen resulting the concrete function that we talked about last class also based on the D type and shape. So, the signatures of the data that is coming into, let us say this x. What is x? Basically a tensor. It will have a data type, it will have a shape, it can be 2D, it can be rank 0, rank 1, it can have multiple several dimensions as well, right. So, now when this function is called with the same number of or same amount of these two features, that means that will be called from the cache directly. If the signature varies, then the graph will be rebuilt again. So, this is the concept. So, you can see that in the call 1, the call 1 is happening with float shape 3, right. So, here I am passing, so this is the function call happening, and the function call happening with tf dot constant. Now, you can see that here we have a list with shape 3, right, float 32 with shape 3. In the second call here we have second call here, and in this second call we are having tf dot constant as shape 3 again. So, you can see that two subsequent calls happening to the same function with the same D type, which is data type of float 32, and same size or shape. So, basically your function which was built and cached, so they are reused here. So, this is the first call obviously, and the second call happening here. So, that means this will be using the cached compiled graph. So, this will improve the performance. But if I do call in the third time, you can see that this call is happening, and the constant that we are defining, the shape is changing to 4 than 3 in the previous call. That means this is a new trace, and this function will be rebuilt again with a new trace. Those shapes changed, shape has been changed in the subsequent calls. So, this is why you need to understand what exactly the signatures I am sending to this particular TensorFlow graph that I have already formed with this tf dot function decorator. Now, in the subsequent call again I have call for new trace, data type changed. So, now my data type has changed to floating 64. Now, it was floating 32 single precision, now I have double precision with the same shape of, let us say 3. Okay. So, shape changed as well as the data type changed, right. So, this is a new trace. Again in the subsequent call I have shaped, right, shape is unchanged, but my data type is float32, right? So it can use the original signature, but because the shape is same. So if you just see the trace calling here, so this is the tracing and caching happening. This is how. So you have the function called decorator, you have the graph 1, graph 2, graph 3. So now this graph 1 has been called with shape 3 at the first call. So call A will reuse G1, right, and shape 3 has been called in the subsequent. So basically you have this reuse of G1 in the next call as well. G2, which is another graph with shape 5 or shape 4 or whatever, and shape 3 you can see float32 or float64, it will have a different shape. So that means if my shape changes, I am basically calling a new graph trace. So that means same shape plus D type usually reuses the same or cached graph. Changed signature will trigger or may trigger. So based on, obviously, if you are increasing the precision or decreasing the precision, because if you decrease the precision, that means you no longer using the same data type, right? If you are increasing, you need to have more space to be allocated, but if you are reducing the data type size, I mean, it does not matter because you have already allocated the size that is needed. So it can reuse. So that's why it may reuse or it may trigger retracing. So retracing can happen, right? So retracing is important, and while you are retracing, that means the call graph that you have already have the cached graph already there, that has changed. Okay. So here we can see that tf.print. So another features that we see here, that the traces, you can see here the traced data type is float32 here shape, traced data type is float32 with shape 4, traced data type float64 with shape 3, and so on and so forth, right? Okay. So now another interesting thing inside the graph that we are forming is tf.print. Now this tf.print will print every time. So you can see here how many time I am calling, right? So let's say this time, so this print is outside, these prints are outside, and when I call the graph, the tf.print is inside the graph, right? So you can see here inside the graph how many times I am printing, right? So inside the graph shape 3, inside the graph shape 3, right? Shape did not change. Inside the graph shape 4, inside the graph shape 3, and inside the graph shape 3. Okay. So which is cached, which is new trace, by using this print itself you are knowing it, right? Now this tf.print is different than print that we are using it here, because this is Python print and this belongs to TensorFlow, and this will be associated with your graph itself. So with your call graph itself, the tf.print or tf.any API that you call will be associated with that particular graph. This trace log is a Python list, right? So it is not associated with the TensorFlow graph. Okay, so each time you call, this will append or may not append based on the data type that you are shaping, and basically the signatures are being called, right? So whether you are tracing or retracing, okay, based on that it will happen. So you need to understand exactly what is the signature. So the input signature, it prevents unnecessary retracing. So if we define that input signature is equal to your, let's say, shape is two-dimensional shape with the size is here none. So that means the shape can be anything here with data type of tf.float32, any 2D float, any 2D with float32. Any 2D with float32, the shape does not matter here, none. So any 2D with different shapes, but same data type float32, if you call, this signature will not change. That's why I have defined this input signature as such, and then this stable function will not go again and again whether the shape is changing, as long as I am keeping the data as 2D. Okay, the shape can be changed, right? So that is exactly what we are seeing here. shape can be changed. So output shape is here 3, 10, 1, 64, 162. So now 5 out of last 5 calls function unstable fn at this triggered tf dot function retracing, and tracing is expensive because if we want to recompile again and again based on the data type that we are sending, it is not good, right? So basically with input signature it will exactly trace once. Otherwise, if we use without let's say retrace log2, which will do this unstable function inside this unstable function happening, right? So this will not do the retracing, so it will trace again and again, and here with the same input signature we can have this stable function running which is let's say running some reduce mean function which will run only exactly one trace will happen based on what exactly we have discussed so far. So how many time you are tracing, that means you are compiling this particular graph again and again, based on that you are creating these traces, right? And this trace will happen again and again for your unstable functions, and that will take long time. Rather we can define one stable function with a particular input signature where we can vary the shapes, but as long as we keep the data type and the size of the tensor or the input signatures are same, so that means we can actually cache or use the cached graph again and again, so it will reduce the invocation time or the compilation time in this particular segment of functions. Now here instead of none and none you can define any data, right? So you can define let's say 4, 5. That means you are stick to the shape that you are defining for this particular 2D tensor. You can increase or decrease the number, or you can put none, which is basically taking any number, and so on and so forth. Okay. Now the autograph will be essential because in the function what we are trying to do, we are trying to create function which has some complicated operations. That means some loop is happening again and again, so some operations will happen again and again, or it will be called multiple times. So loop will be happening, some graph will be happening with branches, right, like if else, some for loop, while loop, or any other branches. So different control flow can be there inside my graph. Okay. Now in Python, how we define the graph? We define by if else structure, we define by for loop, we define by while loop, right? But in this TensorFlow, when we are trying to formulate the TensorFlow graph, that is a bit different. The graph is tf.cond, which is the equivalent of if structure inside your Python. So if I want to make a branch with in this TensorFlow graph that we are making, where we are trying to optimize the function calls, we cannot use if, we have to use tf.cond, or instead of for I have to use tf.while loop. So this is structure that is specific to TensorFlow. As I said just in this previous program, this tf.print is associated with TensorFlow, it is not the Python print. So don't mix these constructs that we write in usual Python and in the TensorFlow. Here is different. So basically autograph converts your Python control flow into TF graph operations. So if we do not want to use this tf.cond, tf.while loop, tf.other loops, so we need to have an automated mechanism which will take the construct of Python and convert it into the TensorFlow operations which will define this graph. So that means that mechanism is called the autograph conversion. Okay. So here is an example obviously in notebooks like Jupyter or Colab, Autograph can read function source automatically. The explicit forms below work in all execution contexts. So either you are creating a script or you are creating a notebook, it does not matter. So we'll try to stick with the standard definition in this following section. So TF dot function, you can see that here under this decorator I have this particular function which is conditional activation. Let's say conditional activation returns ReLU if max x is greater than some threshold. So this is my activation mechanisms, let's say formula. Okay, so this is a conditional activation. So if max tensor x is greater than some threshold value, it will return the ReLU x, or else it will return 0. So basically I have to use if else. Rather, you can see here we are returning tf.con, which is basically your if equivalent inside the TensorFlow graph. Okay, it will reduce the x and try to see whether this is so this is the condition, right, whether this is greater than threshold or not, and it will be returning ReLU, or else it will return the zeros like. So basically here the true function and false function will actually be evaluated. So you can see here the pattern is bit different than the normal if else. If it is written by if else structure, you would have written that if reduce max x is greater than threshold, then you will have this, or else this particular return, right. So this is the tf.con equivalent of Python if. And similarly here you can see that this power series computation, which is under again tf.function construct, which is saying that this will be a TensorFlow graph. So this is the conditional definition, and this is the body, and you can see tf.while loop is used for how many times it will actually loop, and basically the constant starting from 0 to 0 like. So this autograph equivalent is basically doing x to the power 0, x to the power 1 till x to the power n terms minus 1, obviously based on whether k in range, so total plus equal to x power k. Okay, so this is the autograph equivalent. So now you will write this in Python, right. So for k in range, total plus equal to whatever the this series, right. So it will form this particular graph. Similarly here another pattern, which is tf.while loop, which has its condition, the body, and the variables, the count variables. So x out and count out. Here let's say we are multiplying x by 1.5 until some greater than threshold. So we write in while loop, while tf.reduce sum x less than threshold, x multiplication equal to 1.5, which is x equal to x multiplied by 1.5. But here we are incurring this definition, body definition, which will be executed here as body, which is being repeatedly executed based on this condition and this loop variables count, so x till count. So basically this is how tf.while loop, another construct, is there. Okay, and now obviously we can test it by position negation these definitions, and we can see the values. Okay, pattern 2, pattern 3, the values, 6 iterations, final value is this one, this result is this. So all autograph patterns will be verified by these how many let's say final value that we are getting. Obviously this is working, that is the guarantee. You just check the value whether this value is matching this to this particular values or not. So this is just one sanity checking happening, but we get the idea that with autograph we can actually formulate the if else conditions or the loops in the tf.function graph, but these are equivalent of Pythonic if else and for while loops. Okay, so we'll see this full custom training loop in the next segment along with the XLA compiler. We'll discuss with this, we'll conclude this segment. Thank you.